Hello everyone, my name is Abhishek Alhat and today I will be talking about quantum computing, a revolutionary approach to computation that promises to solve some of the most challenging problems. Over the next few minutes, I will walk you through what quantum computing is. Then we will look at why traditional computers aren't enough for certain problems. Next, we will dive into some fundamental topics in quantum computing, which are superposition, quantum gates, measurement, interference, and entanglement. After that, we will explore the idea of quantum advantage, where we will look at potential real world applications in various fields where quantum advantage could make a meaningful impact. Then we will code an interesting problem, and I will practically demonstrate how we can make use of quantum algorithms to solve that problem. Finally, we will wrap up with some concluding thoughts. So, what is quantum computing? Quantum computing represents a fundamentally different approach to computation. While traditional computers process information using bits, zeros, and ones, quantum computers use qubits. What makes qubits special is that they leverage quantum mechanics to perform calculation in ways that classical computers simply cannot. This isn't just a faster computer, it's a completely different way of processing information based on the principles of quantum physics. We will discuss about qubits more in upcoming slides. So now question arises, why do we need quantum computing? You might wonder, why not just build faster classical computers for the computation? Well, the challenge is not just speed, it's the nature of certain problems. Some are inherently hard for classical computers no matter how fast they get. For example, finding prime factors of large numbers. Take a number used in modern encryption, RSA 1024, which has 309 decimal digits or 1024 bits in binary. For such a number, finding its prime factors using classical computers could take thousands of years, or even more than that, even with the best supercomputers. This difficulty is actually the backbone of internet encryption today, but quantum computers using algorithms like Shor's algorithm can potentially solve these problems quickly. Beyond encryption, there are numerous problems in the fields like optimization, chemistry simulation, and machine learning that grow exponentially complex with size. Quantum computers uses quantum mechanics to compute by different rules than what classical computers do. They don't perform operations faster, but they perform different operations than a classical computer, and these operations can sometimes lead to faster route. Now let's discuss the fundamental topics in quantum computing. The first key concept in quantum computing is superposition. Unlike a classical bit that must be either 0 or 1, a qubit can exist in a state that's effectively both 0 and 1 at the same time until we measure it. Mathematically, we represent this as psi is equal to alpha 0 plus beta 1, where alpha and beta are complex numbers representing probability amplitudes with alpha square plus beta square is equal to 1. The important thing to understand is that this property allows quantum computers to process multiple possibilities simultaneously, creating a form of massive parallelism that classical computers simply cannot achieve. Now we will discuss quantum gates. Just as classical computers use logic gates to manipulate bits, quantum computer use quantum gates to manipulate qubits. These gates are represented as mathematical operations that transform the state of qubits. One important example is the Hadamard gate, which takes a qubit in state 0 and puts it into an equal superposition of 0 and 1. The poly X gate that flips the state of a qubit, turning 0 to 1 and 1 to 0, just like a classical NOT gate. Another is the C0 or control NOT gate, which can create entanglement between qubits, something we will talk about shortly. So we can build quantum circuits by combining these gates. For the circuit to be useful, at some point we need to read output, which brings us to our next topic, measurement. Measurement is where the quantum world connects back to our classical world. When we measure a qubit, its superposition state collapses and it becomes either exactly 0 or exactly 1. If a qubit is in an equal superposition, like the arrow pointing halfway between 0 and 1 shown in the image A, it does not mean the value is 0.5. Instead, it means there's a 50% chance of measuring 0 and a 50% chance of measuring 1. We get this from coefficients or amplitudes in the front of x0 and 1 as shown in image B. The probability always sums to 1 because the qubit must collapse to one of these states when measured. So the specific probabilities are determined by the qubit's quantum state at the moment of measurement by the amplitudes. Now, next fundamental topic is interference. Interference is crucial to understanding why quantum computers can outperform classical ones. In quantum mechanics, the wave function of qubits can interfere with each other like physical waves in water or light. When two waves are in sync, rising and falling together, we get constructive interference as shown in image. The waves reinforce each other, making the combined amplitudes larger. This increases the probability of measuring that particular outcome. This is how quantum algorithms amplify the correct answers we want to see. And when two waves are out of sync, one rises while the other falls, as shown in the image, we get destructive interference. The waves cancel each other out, reducing the combined amplitude potentially to zero. This decreases or eliminates the probability of measuring unwanted outcomes or incorrect answers. Interference is the basis of many quantum algorithms and can lead to significant speedups in computations like Shor's factor algorithm and Grover's search algorithm. This allows us to solve certain problems exponentially faster than any classical approach. Last topic and most important topic that we are discussing now is entanglement. Entanglement describes a special kind of non-classical correlation between quantum systems even when they are separated by vast distances. When quantum systems become entangled, they can no longer be described by separate wave functions. Instead, they share a single wave function that captures their correlation. What makes this remarkable is the actions performed on one system immediately affects the other entangled system, regardless of the distance between them. This property is what fundamentally distinguishes quantum mechanics from classical physics and enables the unique power of quantum computing. So, with the combined power of superposition, interference, and entanglement, quantum computers can solve things that classical computers cannot today. Let's now look at quantum advantage, which occurs when quantum computers demonstrate its ability to solve specific problems faster than the best classical computers. While full quantum advantage has been achieved only in limited specialized scenarios so far, its potential applications span in numerous fields that could transform various industries. Like in chemistry and material science, quantum computers can simulate molecular interaction far more accurately than classical computers, potentially resulting in advancement in medicines and material research. For optimization problems like routing delivery vehicles or optimizing financial portfolios, quantum algorithms like the quantum approximate optimization algorithm could find better solutions than existing methods. In machine learning, quantum approaches could enhance data classification, pattern recognition, and feature extraction. In finance, quantum computing could transform risk analysis and portfolio optimization. While quantum computers threaten current encryption methods, they also enable new quantum resistant cryptographic techniques. These examples illustrate the wide scope of impact quantum advantage could bring from transforming how we design medicine and materials to enhancing machine learning and AI systems, as well reshaping industries like logistics, finance, and cybersecurity. So before program execution, let's look at our problem statement. How can we efficiently find a specific item in a large unstructured data set without checking each one individually? We can solve this using Grover's algorithm, one of quantum computing's most powerful and practical algorithm. So now let's open our Visual Studio Code. So Grover's algorithm provides a clear quadratic speedup over classical search methods, making it perfect example for quantum advantage. We will execute our program and do output evaluation using IBM's quantum processing unit. Before moving forward with the code, I will head to IBM's quantum platform. Here in the Compute Resource tab, we can check IBM Brisbane and its specification. We can see it has 127, it is a 127 qubit quantum processing unit. So now we will also be making use of Qiskit, also provided by IBM, which is an open source Python-based software development kit for quantum computing. So now let's start with a problem that illustrates the power of quantum search. I have an unsorted list 12, 8, 18, 27, and I need to find a specific value which is 18 in this case. I have defined what's called an oracle function that acts as our search criteria. It returns true only when it finds our target value of 18 and false otherwise. In real-world application, this oracle could represent complex scenarios like checking if a database entry meets a specific criteria. The oracle tests whether a given input is the solution by flipping its face, but it does not reveal the solution, it just marks it. First, let's examine how a classical computer solves this search problem. Without any prior knowledge about the list structure, the only approach available is to check each element sequentially until we find our target, essentially a brute force approach. As we can see in the output here, we found 18 at index 2, requiring 3 oracle calls. This linear approach is fundamentally limited with n items. We need big of n check on average, meaning the search time grows directly proportional to the size of dataset. Now I will show you the oracle circuit that we will be building. So this is the oracle circuit that we will be building in our program. So when we have two qubits, we can represent four possible states: 0, 0, 0, 1, 1, 0, and 1, 1. Let's say our target or key is 1, 0. That means we will input 1, 0 into the oracle, and as per the design, the oracle will output minus 1, 0. What this means is if the input matches the key, the oracle flips the sign of that state. To make this happen, we use a unitary matrix which we can encode directly into a quantum circuit. Specifically, the circuit we use to flip the sign of the 1, 0 state uses a control Z gate as shown in the diagram below. But that's not all. We also need to amplify the probability of measuring the correct answer, which we do using something called as reflection operator. When we combine the effect of the control Z gate with the reflection operator, the result is what we call Grover's diffusion operator. Now let's implement this quantum solution. We need only 2 qubits to represent the 4 possible indices in our list. This is our quantum oracle implementation, as we discussed in our diagram. We start with a 2-qubit circuit named oracle. The first X gate on qubit 0 inverts its state. This is necessary because we need to set up the exact condition that corresponds to our target index. In the circuit below, the CZ gate in the middle performs the critical phase flip operation when the qubits are in the specific state that represents our target. The second X gate returns qubit 0 to its original state, ensuring we have only applied the phase flip to our target state. This specific configuration ensures that only the state 1, 0 receives a phase flip, marking it as our solution. The second essential component is the reflection or diffusion circuit. This is most important in Gross algorithm as it transforms the phase difference into a measurable amplitude difference. Here we are implementing a sequence of operation. First, Hadamard gate on the both qubits transform our states into a different basis where the reflection can occur. Next, Z gate and a control Z operation performs a reflection around the average amplitude of all states. Finally, Hadamard gates transform back to our original basis. This reflection operator is important as it amplifies the difference between our marked state and all other states. It increases the amplitude of our target state 1, 0 while decreasing the amplitude of the non-target states. This ensures that our target state will have a significantly higher probability of being measured. Without this reflection step, the phase flip alone would be undetectable, which is why these two operations always work together in Gross algorithm. Now we combine everything in our complete grower in our complete grower circuit. We start by applying Hadamard gate to create a superposition of all possible states. Then we apply our oracle, which marks the target state with a phase flip. This encodes our search criteria. Then we apply the reflection operator, which amplifies the mark state. Finally, we measure the qubits to collapse the superposition, and read out our results. We can see this in the circuit diagram below. Now, one thing to notice here is that we are using 1024 shots. So we ran this algorithm with 1024 shots. In quantum computing, a shot refers to a single execution of the circuit that results in a measurement. By running 1024 shots, we can identify the most frequently occurring result with high statistical confidence. So in the output, we can see that for our quantum search result, state 10 has appeared 937 times. That's about 91% probability, which is the highest. So the binary value 10 corresponds to decimal 2, which is the index containing our target value 18. We can also cross check this by checking our list. So in our list defined, we have 18 at index 2. So we have found the location of our element 18 at index 2. This distribution also shows other results. Like for state 11, the count is 63. For 00, it is 20, and for 01, it is 4. These represents the remaining quantum probabilities distributed across non-target states. These measurements directly demonstrate quantum interference at work. Grover's algorithm uses constructive interference to amplify the amplitude of our target state 10, while simultaneously using destructive interference to reduce the amplitude of non-target states, which are 11, 00, and 01 in our case. So we have successfully executed our program on IBM's quantum processing unit. To summarize the quantum advantage with corresponding to our program, our classical search required 3 oracle calls for a list of 4 items, which is of big of n scaling. Grover's algorithm achieves the same task with big of square root of n oracle calls, a quadratic speedup. This becomes important at scale. For a million item database, classical search will potentially require 1 million operations, where Grover's algorithm will approximately require 1000 operations, 1000 times faster. This demonstrates why Grover's algorithm is considered an important quantum algorithm. It provides a mathematically proven quadratic speedup. It's applicable to many search and optimization problems across industries. Also, it showcases fundamental quantum principles like superposition and interference. Finally, it demonstrates a fundamental quantum advantage that can't be achieved classically. To conclude, quantum computing isn't simply a faster version of today's computers, but a completely different approach to solving problems. Quantum computers think differently than regular computers, making them better at certain tasks but not a replacement for everything. Looking ahead, quantum computing will certainly change fields like security, medicine development, and artificial intelligence. We are getting a clearer picture of where quantum will make the biggest difference, helping us prepare for the coming challenges in computing. I appreciate your time today as we have explored the fascinating world of quantum computing and its potential to reshape our technological future. Thank you so much for your attention.